Edge ST6 introduces design optimization, providing designers with the ability to set up what-if operational scenarios to automatically predict how a part will react to specified loading conditions. This innovative functionality helps to develop safe and reliable products at minimal costs. In this demonstration, we'll study a sheet metal bracket which supports the motor and gearing for a garage door opener. We'll open the 5mm thick sheet metal bracket in Solid Edge and view the results of a previous analysis. A 0.19mm deflection of the bottom flange was computed, evidence the bracket is very stiff and therefore over-designed within the defined loading conditions in sheet metal gauge. Our goal here is to minimize the bracket's material while still providing a safe product. For the existing simulation study, we'll use the new optimization option to set our design objective. In this case, we wish to minimize the mass of the bracket while keeping the deflection less than or equal to 1 mm. We'll restrict the thickness of the metal to a range between 1 and 5 mm. Watch as Solid Edge iterates on various thickness values within that range. We could do this manually by changing the sheet metal gauge, solving the study, looking at the results, then repeating this process until we have an acceptable solution. But this could take hours to perform. With the optimization functionality, convergence on a solution takes seconds. When we review the results section of the summary spreadsheet, we can see that Solid Edge converged on a thickness of 2.93 mm, resulting in a deflection less than 1 mm. This convergence on thickness can be confirmed by looking at the graph of the bracket's mass iterations. Notice how the graph levels out in the final 2 of the 7 computations. Now that we have an actual thickness of 2.93 mm, which represents a minimized but safe amount of material, we can use that to guide selection of an available sheet metal gauge. As we search the Solid Edge material table for a thickness gauge, the closest we'll find is 12 gauge, or actual thickness of 2.77 mm. For purposes of safety, we'll move up to a 10 gauge sheet metal gauge, which represents an actual 3.58 mm thickness. We'll apply that to the model, resolve the study, and find that this new thickness results in a deflection of 0.54 mm, meeting our requirements to stay below 1 mm. With the inclusion of design optimization tools in Solid Edge ST6 simulation, designers can reduce their material and engineering costs with confidence that safety and reliability goals are being met, all before building a prototype. Solid Edge. Design better.